Well, for test 3 material, we have fluids, we have oscillations, and we have sound. And so those are going to be the 3 major areas. And so for today, we're going to do a lot of fluid stuff, probably going into about 45 minutes into tomorrow. And then oscillations and sounds for the rest of Friday and then Monday. And then that's all the new material we got. New problem set out. That problem set 7 is due Monday at 6 p.m. We do not have graders, or we do not have tutors available today or tomorrow, but they will be here on Monday. So let's talk about fluids. We've already introduced the idea of density. And density comes in 3 shapes: linear, area, and volume. Now, we're familiar with volume density, and we typically just say density. Density is the common usage of volume density. Area density and linear density are just mentioned as linear density and surface density. Now, volume density, we're all familiar with that. Volume density is listed as rho, and it has mass over volume. When we're doing problems with fluids, this equation is used frequently. A lot of times you do these problems and you get to a point where you're like, I don't know what to do. And just throw in rho is m over v and see what sticks. Is typically my little pet phrase for it is, it's the Swiss Army knife of equations. A lot of times, when in doubt in a fluids problem, see if you could stick that in there. And it's the most common of the densities. You've got a volume, you've got a mass, take the mass divided by volume, boom. You could find the density of this podium. You could find the density of a person. You could find a density of a ball. Just take the ball, figure out its volume, get its mass, now you got density. Now, area and linear densities are a little bit of a, technically the tile on the floor has a volume. It has a very small thickness, but it does have a definite area. And so it's easier to measure a tile's area than to try to figure out its volume. So what area density is, and we use sigma, is just mass over area. If you have 100 kilograms of tile and you know that the room is 100 square feet or 100 square meters, keep the units consistent, then you know its surface density is 1 kilogram per square meter. It's easier to measure the area of a flat tile than to measure its volume. It's just easier. Yes?
How did you say that for the area density?
It's sigma. This is one of the things, like, I can't do it because technically I think it's either harassment or torture of the student. My fraternity, when I was a pledge, they did this to me and then we did it voluntarily, so then I guess it wasn't torture. We'd take a match and then we would say the Greek alphabet. The alpha, beta, gamma, delta, epsilon, zeta, eta, theta, etc. And you had to say it before the match went down and burned your fingers. And then a few of us, including myself, it does explain a lot, this was voluntary. We would take the lit match and hold it upside down and then say the alphabet, because then that adds a little bit of a time restriction. You can get that match to hold it for a pretty long time, but upside down, you better move when it comes to saying it. So you got very familiar with the Greek alphabet. This is a lowercase sigma. The uppercase is usually like this, but for area density, we say sigma. For linear density, it's lambda. And what's really funny about the whole match thing is I told one of my classes during a regular semester, and they had a talent show, and the dude won the talent show at his fraternity with the match thing, because they'd never seen it before, and I was like, yes, that's my student. I'm so proud of you. So M over L. Linear density, you can, the advantage of linear density is try to figure out the volume of 100 meters of guitar string. It's just unwieldy to figure out the full volume of the string. So what people do is they go, well, it's this long, it's got this mass. It is a more easily measured value. And so those are the three: lambda, sigma, and rho. And just for full disclosure, I was the pledge educator. That should explain a lot. So, how well I enjoy torturing students. So this, for fluids, we're going to be using volume density. And fluids, solids, three-dimensional objects, those we should all be familiar with. Basic geometric shapes will be used. Now, for circle, area, circumference, cube, sphere. Hold on, I can't even spell sphere. And cylinder. So all of these have just the basic areas and volumes and circumferences. The thing that you need to remember is I don't give the basic geometric shapes in the equation section of the test. This stuff you should just know by heart. Why is that? Because you're a human, you're at least 18 years old, you got a brain between your ears. There was one particular summer class which basically complained to the ends of the earth, please give us the basic shapes. I said, okay, fine, but the deal is this: the next time I go to my doctor and I ask her a question, and if she answers the question, what's the volume of a cylinder, correctly, I'm never including those equations again. And they accepted it because they didn't care. They totally threw you guys under the bus. And so I went to my doctor and she said, do you have any questions? And I'm like, anything? I can ask anything? She's like, yeah. And I go, well, what's the volume of a cylinder? And she goes, pi r. And she eventually got it out correctly. And she hadn't been taking this course in like 25 years. So if she can remember it, you can too. So basic shapes like this. I don't expect you to know the volume of a pyramid or the crazy stuff. Just basic circle, cube, sphere, cylinder. That's all I really need. Well, let's take a look at, we have a cylinder of a material, and it has the following features. It has a density of 2,000 kilograms per cubic meter. Now, the typical, and actually the material, I will introduce the name now. It's called rebellium. Now, rebellium is my fictitious element. If I get lucky enough to invent an element, I'm going to name it rebellium. I know, stunned you as well. So with rebellium is my generic element that has the properties of whatever I want it to be. Is it a gas? Is it a solid? Yes. Is it dense? Is it light? Yes. It's whatever I need it to be. So there was one tutor who told the students, look it up in Wikipedia, you could find the density of rebellium in there, and they just went running. And I'm like, well, good luck finding that. If you find rebellium's density, let me know. So the density is 2,000 kilograms per cubic meter. It has a radius of 2 meters, and it has a height of 5 meters. And the question that I have is, and it's a whole bunch of questions, the first of which is, well, what's the mass? So we have to use our Swiss Army knife equation. Rho is mass over volume, so mass is rho times volume, which is 2,000, and then volume is pi r squared h. So pi r and h, 5, and this means what do I have? $12,566 kilograms. So the mass of that object. So you can get all sorts of stuff. With this one equation here, and rearranging it, you can define mass, density, the radius, the height. You can take all sorts of things with this. Another question. What is the force of gravity of that cylinder on the ground? And this becomes, the force of gravity is just mass times gravity. So 12,566 times 10, or 1.26 times 10 to the 5th newtons. And so that's some basic stuff, some that we've dealt with before, and coupled with now the density. We now need to introduce a new idea. We've had position and time, and when you mix those together, you get velocity. When you mix velocity and time together, you can get acceleration. When you mix acceleration with mass, you get force. And now we're going to take force and mix it with area, and this is where we get pressure. So starting from basic principles, change in position with respect to time is velocity. Change in velocity with respect to time is acceleration. Acceleration times mass is force. And now we have pressure is equal to force divided by area. So what are the units of pressure? The typical units of pressure, well, force is a Newton. Area is a meter squared. So it's a Newton per meter squared is the concept of pressure. Now, 1 Newton per meter squared is what they call 1 Pascal, which is shortened to PA. So just like you could have kilograms meters per second is a Newton, you could also say a Newton per squared meter is a Pascal. Another conversion that we have is 1 atmosphere, the pressure that we're experiencing now, is 1.013 times 10 to the 5th newtons per meter squared. You will be given that number in the equation section. When I was an undergrad, I didn't know that number. How do I know it now? Because I've said it 25,273,875,001. When you say it enough, long enough, it just sticks. I don't want to know this number. I could look it up. I'm not a botanist. So with this, eventually it just sticks. That's a conversion. Typically we use atmospheres because it is more easily understandable. We all understand like the pressure of the air. Really, when you think about it, air is a fluid. We can't really see it, but there are a bunch of little particles that are all just moving around, resting on top of us that go up several miles. The atmosphere is, well, at least a couple tens of thousands of meters. They're all pushing down on us, much like the steel cylinder pushing down on us. Now, with pressure, we have force divided by area. So naturally, I'm looking for someone with open to understand. All right. Now let's say for an instant, you know I'm not going to hurt anybody in class. I just annoy animals and kill pop stars. You're not a pop star, are you?
No.
Okay, good. So basically, I can do this. I could slam my foot down on his foot, and that would hurt. Now, what are the two ways that I could change things to make that hurt more?
Decrease the area.
Decrease the area. Now, how would I do that? I could put a spike on top of your foot and then slam down on it, because that decreases the area. The force over a small area is a great pressure and would probably puncture the foot. The other thing that I could do is hit it harder. So greater force, greater pressure. Greater area, lower pressure. So that's why, like, I mean, you step on, say you had a Lego that was like 3 feet by 3 feet, and you stepped on it, that doesn't really hurt, because it's the Lego is underneath your entire foot. You step on one of those little Legos that are just the 1x1s, and the area is so much smaller. So the pressure is a lot higher, and the pain factor is. And we're starting to introduce the idea of if force increases, pressure increases. And this introduces the idea of directly proportional. If you double the force, you double the pressure. Triple the force, you triple the pressure. The other thing is, if you increase A, you decrease pressure. And this means it is indirectly proportional. So those are new, or two new phrases or two words that we need to.
What does that say? The before area?
Oh, that's just a scribble. I was going to write A and then I wrote F again, and I was like, no, that has to go. So we have the idea of pressure, what pressure is, what its units are. What's the idea of directly proportional and indirectly proportional? Just throwing out an example, the position equation is x equals 1/2 at squared. The position is directly proportional to acceleration. If you double acceleration, the position is increased. Now, let's go back to that steel cylinder problem, which has a mass of 15,000, whoa, not that, 1.26 times 10 to the 5th newtons. The radius of this thing was 2. So the question is, what is the pressure of the cylinder on the surface? Sort of like, I mean, the cylinder would be my cup. What is the pressure of the cup, or this big cylinder, on my hand? Well, that, you know what pressure is. It's just force over area. You've got the force, 1.26 times 10 to the 5th newtons over area, pi times 2 squared, and we get an answer of 10,027 newtons per square meter.
That's not the area.
I have a question. So either A, I gotten it horribly wrong, or B, so what is the cylinder? Cylinder rests on its circular end. Who's the one who challenged me? Okay. So this water bottle, I don't think you're safe because you're in row 5. The cylinder is resting on the table. What's the area of that cylinder that's resting on the surface? It's the area of a circle. So that area, pi r squared, or pi times 2 squared. Does that answer? You feel better? Okay. I'm only here to help.
So wait, why are you using the area of a circle? No good.
All right, okay. Now the second person, now it makes me believe I haven't communicated properly. So you have a coffee cup that has a certain amount of gravity force. And it's resting, on what side is that coffee cup resting? It's resting on the circle. If it was resting on the side, you would have, it's the area of contact with the ground. So in this case, it's a circle. If it was a cube, it would just be L squared, one side of the cube. If it was a pyramid, it would be whatever the base of the pyramid is, and I'm not going to go into that. So whatever it is. With a sphere, I would give you a sphere because it's just resting on the point of contact. So do we get this?
Yes.
All right. Right now, what's the pressure of me on the floor? 2 times the area of one of my feet. Because all my weight is coming down on those feet. Now let's look at another way to determine the pressure of the cylinder on the ground. Pressure is force divided by area. Well, that's obvious. I just gave the answer. Or I just gave you the definition. Force is mass times gravity divided by the area. Well, we look at what does mass mean using the Swiss Army knife of equations. Density is mass over volume. So mass is density times volume. Substitute that in there. Density, volume, gravity over area. Cylinders, its volume is pi r squared h. Or more generally, the base area times its height. Substitute that into here. Rho A H G over A. The areas cancel. And you get rho H G. So what we have just shown you, the area of an object is not critical or essential to finding the pressure. Density, height, and gravity are. Those are critical. If right now, if we have a cylinder of water like this, and we have a smaller cylinder of water like that, both have the same height, that the pressure there would equal to the pressure there. As long as the H's are the same, well, the H's are the same, the density of the fluids are the same, and the gravity influencing are the same, then those pressures are the same. And you could even take a look at, if we had a tank of water and a bowl, and we measured the pressure there, and we measured the pressure there, and both of them are under height h, that P1 is equal to P2, as long as the depths are identical. So we could even change it so that it's like a tube, and on one side of the tube it has a big opening, and on the other side of the tube it has a smaller opening, and those 2 points, or these 3, are all studied. All pressures are equal. In fact, you could say that the pressure there and there are equal. And so what I've introduced is the concept of Pascal's principle. That if you have a pool of fluid, and as long as the depths are the same, the pressures are equal. And this can be taken advantage of. One of the ways that we take advantage of certain things is, or we take advantage of Pascal principle, are hydraulic systems. What's a common hydraulic system that you deal with every day? You may have heard something talked about your brakes called the master cylinder. Your braking system is just a big set of fluids pushing down hard. Like, what you notice is when you push down on your brakes, inside the brakes there's a cylinder or a piston that pushes down on hydraulic fluid that has a very small area. And then if you've ever seen the tires taken off and they're changing the brake pads and stuff, those brake pads are big, like that big around. But the little cylinder that you're stepping on is very small. And what that does is it allows a very small force on one side to create a very large force on the other. Another hydraulic system that is quite common are the hydraulic lifts when you drive your car in to get its oil changed. They hit a button, a little motor runs, it lifts this huge car up off the ground. And how are they able to do it? A cylinder is pushing down on fluid on one side and creating a greater force on the other. So in our particular case, on the right-hand side, we have a 2,000 kilogram car, and it is resting on a plate that is 20 square meters. So over there on the right-hand side is a 2,000 kilogram car. The area of the plate the car's resting on is 20 square meters. Over here on the left is a plate. The area of the left plate is half a square meter, something dramatically smaller. The question is, how much force is necessary to be on that left plate to balance out the 2,000 kilogram car on the right. In fact, what I'm going to do to make it a little bit more comparable, all I want to know is how much mass do you have to put on that left plate in order to balance it. Pascal's principle says that the pressure on the left is equal to the pressure on the right. Pascal's principles start with that. You see a hydraulic problem drawn like this, you're going to get Pascal principle ready to go. Pressure on the left, force on left, area left, force on right, area right. So those things are set up that way. Force on the left, mass on the left, gravity over area. Force on the right, mass on the right, gravity over area of the right. Gravities cancel. Mass on the left, mr al over ar. So this becomes 2,000 0.5 over 20. 2,000 divided by 20 is 100. 100 times 0.5 is 50 kilograms. So a 50 kilogram mass resting on the left plate can balance a 2,000 kilogram car on the right plate. And so it is all because of Pascal's principle. The pressures have to be the same if they are at the same depth. Now we mentioned pressure of fluids, and we need to introduce the idea of gauge pressure and total pressure and the whole idea of partial pressure. When using a pressure reader on a tire, you are reading gauge pressure. Now, gauge pressure is the extra pressure over atmospheric pressure. So when you read, let's say, I forget about the unit, what their unit, they use pounds per square inch, which is, okay, fine. But let's say you had a gauge that read in atmospheres. And you put that gauge on your pressure, or on your tire, and that pressure came out to be 2 atmospheres. The pressure's total, PT, is equal to PG plus 1 atmosphere. So the total is 3 atmospheres. If that tire is just lying open, like had been torn open, the pressure of the air inside the tire is 1 atmosphere. But that tire needs to hold the car up, so they have to have extra pressure in it so that the tires don't collapse. That extra pressure, the pressure keeping the tire inflated and keeping the car up off the road, is the gauge pressure. So when I say the gauge reads 2, what is the total pressure of the tire? You just add 1 and say 3. Simple enough. So gauge pressure is not a total pressure. Gauge pressure is a partial pressure. So one of the things I like about teaching fluids is I learned scuba diving in high school, and throughout my college years, whenever I go and visit my family, we would go and scuba dive even more. And it was really interesting because we didn't scuba, well, we scuba dived twice in the Gulf, but my parents lived on Hawaii, Guam, all these specific locations. And so I would go out there and we'd go investigate interesting stuff. How does this relate to total pressure and partial pressure? Well, if you are a scuba diver, here's my bad picture of a scuba diver, and you are underneath, let's say the height is 30 meters. I want to know what is the total pressure, and I want to know what is the pressure due to water only. The pressure due to water only, since we have shown back here that all that matters about the pressure is the height of the fluid above you times the fluid density times gravity. That it doesn't matter if it's a cylinder, a rectangular block of water. All that matters is how much water is directly above you. The pressure of the water, therefore, is density of water, Hg. All of the densities that I give you will be on the test, or I'll ask you to solve for them. The common one, water, the density of water is 1,000 kilograms per cubic meter. That's the density of water. So 1,000 H 30, gravity 10. So it's 3 times 10 to the 5th newtons per meter squared. If we convert this to atmospheres, it's a little bit under 2, or I'm sorry, a little bit under 3. 3. .96. There will be questions in the multiple choice that will simply ask, you're 30 meters underwater, what is the pressure on you due to the water only? And it will just give you whole numbers. 1 atmosphere, 2 atmospheres, 3 atmospheres, 4 atmospheres. 2.96 is close enough to 3 that you can just say 3. The rule of thumb is for every increase in depth of 10 meters, the pressure on you increases by 1 atmosphere. So if you're 30 meters underwater, the pressure of the water on you is 3 atmospheres. 20 meters, 2 atmospheres. 10 meters, 1 atmosphere. Yes?
How do you know, whenever you ask for density, how do you know which density equation to use? Like linear density or area density?
Well, typically if it's a fluid, it depends on what its dimensions are. If it's a 3-dimensional object, you use rho. If sigma, we almost never use. Sigma, we may use in 214. Lambda is when we're using like string. This isn't string. It's liquid, so we have to use rho. So now the question comes to, well, what's the total pressure? The total pressure is the pressure of water plus 1 atmosphere. So 30-meter depth, total pressure is 3 plus 1, or 4. And where does that come from? Because when you're at the surface, what's the pressure at the surface of the water? 1 atmosphere. The atmosphere of the air above you. When you go underwater, not only is the water pressing down on top of you, but also the air pressing on top of you as well. So at sea level, 1 atmosphere total. 10 meters, 2 atmospheres. 20 meters, 3, and so on. So when you're under a depth of 30 meters, you know that you've got a total pressure of 4 atmospheres on top. And what's the interesting thing about biological systems? The deeper you go, our lungs are not built to absorb nitrogen easily unless we're experiencing heavy pressure. So the deeper you go, the more nitrogen dissolves into your blood. One of the reasons why divers have to go up slowly if they've been down for a long time is that if they rise too quickly, the dissolved nitrogen in your blood will go back into being gas in your bloodstream, which is not a very nice thing to do. So if you slowly decrease your pressure, your lungs can slowly bleed out all that gas. So that's total pressure, partial pressure, gauge pressure, depth of pressure. I'm trying to think of anything else that I need to cover for that part. All right. Another idea that we have to cover is buoyancy. And buoyancy comes from, if you have, as an example, being in Mobile, Alabama for so many years, you try all sorts of things, just playing around in the pool. We would take a paint bucket, pull it under the water, and this paint bucket would be upside down, so we would trap air in the bucket, and we would pull the bucket down and swing it under the ladder. Let go of the bucket, so the bucket is pushing up under the ladder, and then my brother and I would take turns playing submarine, and we would go under and stick our head in the paint bucket, and we could breathe underwater. And we'd have to recirculate the air every once in a while. But the thing that it demonstrates is when you have the bucket above the water surface, all you feel is the force of the bucket coming down, the force of gravity. If you pull the bucket partially down, you feel a substantial buoyant force. In fact, when compared to the force of gravity, that buoyant force is significant. What the buoyant force is, the water wants to be in the lowest position possible. Just like students, it's lazy. It just wants to settle to the bottom. Now, in order to do so, there's this pressure pushing up the air from being there. As you increase the bucket, now I've seen a few nods, so you guys have done this too. When you've got a bucket and you got it upside down and you pull it underwater, the more of it that's underwater, the stronger the buoyant force. The pressure increases, or the force increases, until if you manage to get that thing completely submerged, that's as big as a buoyant force that you're going to get. If you can get that thing completely underwater, that's as hard as it's going to be. So, non-existent, existent, and growing, and then once it's completely underwater, it is done. So there is a relationship between this buoyant force, the force that's trying to push this object up, and its volume and gravity, and then the fluid inside. This buoyant force is the density of the fluid, the volume of displacement times gravity. So let's talk about those parts right now. The density of fluid is not related to the object density. It's the density of the fluid being displaced. So if you have, this is the bucket and water, not bucked, I don't know where that came from, hold on. And water, this density is not the density of the bucket, and it's not the density of air which is in the bucket. It is the density of the water being displaced. Now let's say that the volume of the bucket is 1/10 of a cubic meter. V sub D, oh, and then another example. If we have a balloon, like a helium balloon in air, the density of fluid is the density of air. That's the density of the fluid being displaced. So you've got to understand the density. What is the fluid being displaced? Is water being displaced? What fluid are we displacing right now? We're all displacing air. So on each of us is a very slight buoyant force from the air on us, trying to lift us off the ground. It's only because it is outmatched by our force of gravity. V sub D is the volume of fluid being displaced. V sub D is the volume of the fluid being displaced. Here, that volume of displacement is 0. The bucket is out of the water. So if the bucket is out of the water, the volume of displacement is 0, so there is no buoyant force. Here, the buoyant force has a significant value, but the volume of displacement is less than the total volume. So if the bucket is 0.1 cubic meter, for this value here, the volume of displacement that you use is going to be between 0 and 0.1. Now, what value is it? It doesn't really matter. But you do know that the volume of displacement can never be bigger than the total volume. Once that object is completely underneath the water, it has its maximum volume of displacement, so that volume, the buoyant force, can never increase. So it looks like well, actually, that part isn't there. So it just goes up, 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 and then it stops because V is the biggest value that you can get. If we were using H with buoyant force, it would go up, and then once it reached a point where over here to the left, the volume of displacement is less than the total volume. Over here, the total or the volume displacement is equal to the total volume. So this is the graph that shows you the force that you feel. When you put that thing in the water, that force increases, increases, increases. Once the thing is fully submerged, then that buoyant force tops off. It maximizes. It doesn't get any bigger. Now, an example, well, this is something that we need to talk about. In Test 1 and Test 2 material, we've used the concept of translational equilibrium, the fact that the sum of the forces in the vertical are equal to 0. Now, in buoyancy, there are terms such as neutrally buoyant, positively buoyant, and negatively buoyant. So those three terms, neutrally, positively, and negatively buoyant, just have to deal with how the vertical forces add up. In neutrally buoyant, it is the sum of the forces vertical is equal to 0. So if you have an object underneath the water, it has a buoyant force pushing up and a gravity force pushing down. If both of those are equal to each other and the forces add up to be 0, then it's neutrally buoyant and it just sits there. A lot of time, if you had a balloon and you let it go and the balloon would just sit there and float through the air, that is a neutrally buoyant object. Positively buoyant, the sum of the forces vertically are greater than 0. So you would have a buoyant force and like a small force of gravity, so there is a net force up. And then the idea of negatively buoyant, the sum of the forces in y are less than 0. So you have buoyant force coupled with a larger gravity force. Here, it would be level. Positively buoyant, the force would go up. Negatively buoyant, the force would go down. Now, one of the greatest demonstrations that I've seen of the definitions of neutrally, positively, and negatively buoyant were a series of experiments that my brother and I did in Guam. He later repeated the experiments off the coast of Costa Rica. In both locations, there are things called pufferfish. There's some in the Atlantic, but this particular kind was in the Pacific. Pufferfish, if you frighten them by grabbing onto them, they will suck in a lot of water and they will blow up. Normally they just kind of look like a deflated balloon that's full a little bit. But if you frighten them, they'll just go, they got a water bladder inside and they suck in all this water and it puffs them up, and they have these little spikes on the outside which are a defensive mechanism. So what we do is we bring gloves, which we normally do because we're handling coral a lot, and we would grab them, and the fact that you're grabbing onto them, they get frightened, and then so they suck in water and they blow up to kind of like a ball about like that size. What we do, and now at that particular moment, they've got water in them, so they have a significant amount of mass inside them, and it is balancing out the fact that their buoyant force, because they have a bigger volume, they have a bigger buoyant force, but it all balances out, and so they are neutrally buoyant. When you frighten a pufferfish, their steering capabilities go out the window. They're just a big ball and they float around and go, ooh, I'm so scary, I got all these spikes. But we've got gloves, so we can overcome that. And then what you do is, one of us would hold the pufferfish face down, and the other one would take their air regulator out of their mouths, put the air regulator up to the fish, and then hit the manual blow button. Now what that does is it drains out all that water. And so now it's being replaced by a whole bunch of air. So the mass and gravity, the gravity force is very small, and the buoyant force compared to the gravity force is now very big, which means this fish is now positively buoyant. And so what do you do when you have a positively buoyant fish and you're there to amuse yourselves? You let go. It's like a balloon filled with helium. It just starts going just right up to the surface of the water, just like a little rocket ship. Because it's lighter than water, its buoyant force is significantly greater. So it just flies up to the surface and then deflates. And when it deflates, the volume of the fish decreases significantly. Its buoyant force has gone down significantly. The force of gravity of the mass of the fish is still there. So what happens is the fish now is negatively buoyant, and the fish will then descend to the bottom where two giggling teenagers are, and then we repeat the process. The fish was positively buoyant, it was positively entertaining, and we would do it over and over again. Yes?
Wait, so is it kind of like if you have the bucket and you push it underwater, and then you have the buoyant force, but then if you flip it up, like when the water comes in, would that be negative?
If you had the bucket and then you, in the water, and then you flipped it over, the air would release. And so then all you would have is just the mass of the bucket. Because the bucket is a weird comparison because the fluid, the volume of displacement of the bucket in air is far less now that you've flooded the bucket. Actually, the flooding of the bucket is a lot like the fish sucking in all that water into its water bladder.
Would be positive?
No, it would be neutrally, the bucket would now be neutrally buoyant. Because in the volume of the bucket, whereas before, you just had the mass of the bucket pulling down, now you've got the mass of the bucket and all the water inside pulling down. That total force is now balancing the buoyant force, and so the bucket will just kind of sit there, much like the pufferfish full of water. That's effectively what you've done. And we did that to the pufferfish again and again for years. And eventually my brother said they get used to it, and sometimes you go up to them and the pufferfish just looks at you and goes, no, I'm not going to play your game. I'm not going to blow up. I'm just going to sit here and do nothing. And I said, well, what do you do then? And he goes, well, you take your thumbs, you put them over their eyes, and then you shake them, and then that shows you whose business or who's boss, and then the fish blows up again, and then you repeat the process. So he never, there was no fish blinding. It was just annoying these animals. And now we know who is the fish of fury. It's that pufferfish, and it's angry. So that, someone told me that last fall, and I was like, oh my goodness, that's true. The truth has now come through. The fish of fury is that pufferfish that we've been torturing for years. So, and now he is. So for neutrally, positively, and negatively buoyant, we've got to use the buoyant force. And while I'm standing up, I'll go back to the class and ask them a question. This question is typically asked in the multiple choice. So we've got the pool in the Turner Center. Ooh, don't shake that. We have a big block of gold. Now, first off, if you got that bigger block of gold, we're going to sell it and get out of here. But let's say we had a cubic meter of gold, which is kind of dense. I don't know the specific value, but let's just say it's 11,000 kilograms per cubic meter. And let's say over here, at the bottom of the pool, I've got a cubic meter of aluminum. If anybody says aluminum, they're failing. So you've got a cubic meter of aluminum. The density of aluminum is, let's just say, 4,000. So the density of aluminum is 4,000. The density of gold is 11,000. They're both resting at the bottom of the pool. The volume of each is 1 cubic meter. Which one has the greater buoyant force? Is it the gold because it's denser? Is it the aluminum because it's lighter? Think about it. I told you the answer. Effectively. What's the buoyant force? Density of the fluid being displaced. Are both of them displacing water? Yes, they're at the bottom of the same pool. What is buoyant force also dependent upon? Gravity. Are they both on the planet Earth? Yes, because they're in the same pool in Turner Center. That just leaves one last number, volume. So both of them have the same volume. Both of them are displacing water. both of them are experiencing the same gravity. So their buoyant forces are not zero. You said it confidently. I respect you. But they're equal. So if you've got that, did you get it right? Okay, good. Why didn't you say so?
I just whispered.
Oh, you whispered. Okay. Now, the types of buoyant force problems that we get are something like this. Trying to think of an easy one. So in our tank, we have a sphere of foam where the density of the foam is 400 kilograms per cubic meter. And we have a volume of 30 cubic meters. So I'm going to give you the volume. So we're not going to play with the radii and stuff like that. It is tied to the bottom of the pool by a string. What is the tension of the string? Now, it's tied to the bottom, which means this thing is in translational equilibrium. It's not going up or down, it's remaining the same thing. So the sum of the forces in Y are equal to 0. Because you could just look at it. The fact that it's not moving means that the sum of the forces in Y are equal to 0. Well, let's draw a force diagram showing what's going on here. You have the buoyant force pulling up because the water wants to get that globe out of the way, and so it wants to push it up with a buoyant force of rho vg. Pulling down is the tension of the string. Now there's one more factor in this problem, and that is the mass of the foam times gravity. Because the mass of the sphere has a significant portion of force, so you have to take that into account to figure out tension. Well, let's do this. Sum of the force. Well, we've got this already. That means we've got FB minus T minus mass of the foam times gravity. I'm looking for T. T is buoyant force minus mass of the foam times gravity. Well, I don't have the mass of the foam, but I do have density and volume, and that means Swiss Army knife time. So density of, buoyant force is rho water Vg. I write V instead of V displaced because the object is fully submerged. Mf becomes density of foam volume. This is the object's mass, so we have to use the density of the substance that is making up the sphere.
Why did you put VG? What did you say?
Oh, I haven't put a G. I need to put that in to make it right.
I mean, but why? Like, why is it a G and not D? Like,
Why is it a G and not D?
Like, the volume of the fluid being displaced. What is the...
Oh, I did not put a D in. Now, technically, I could put that. and then leave that blank because that's still the volume of the object. But because it's submerged, V sub D is equal to V.
I got it. Thank you.
You're welcome. This means you use 1,000, 30, 10, minus 400, 30, 10. Now really it's 600 times 300, or 18,000, I think. No, 180,000. And that's the force of the that's the force of the string. Now what we're going to do is we're just going to riff on this problem in a few different ways. The other thing that we could do is we could partially expose we could just lower the water level. So there is a portion of the sphere which is above the level. I say that the tension is now 60,000 newtons. It's the same foam. It's the same volume. But the question that I want to know is, what is the volume of displacement? How much of the sphere is truly underneath the water? And so you set it up the same way. Sum of the forces in y are equals to 0, which is equal to FB minus T minus MFG. Now FB is now density of water, volume displaced times gravity. Not the total volume, the volume displaced. Why isn't it total volume? Because it's not submerged. Minus T minus rho FVG. That one does have a V because we're thinking about the mass of the entire object. Now I look for volume of displacement. T plus rho FVG is equal to rho WVDG. Divide both sides by rho WG. Equals VD. Now, had this tension term had a factor of G in it, we could just go cancel, cancel, cancel. But since the T does not have a factor of G, we do not cross anything out. So this makes it 60,000 plus 400 times 30 times 10. Hopefully that will give me a number that works out fine. Rho water 1,000 times 10. Oops. Use the wrong symbol. Oops, and I can't do that. Hold on. We haven't. I'm going to change I'm going to change that value to 120,000 newtons. So I'm just going to change that number. This is the main problem of dealing with dynamically created problems, is that sometimes the oh, hold on. I take it all back. No, I'm keeping the whole thing. Now, why? Now, initially I was worried because I thought I had gotten a negative number, but I'm adding this stuff. Oh, please. We haven't. I'll keep it the original. I had made the mistake. Nah, deal with it. Okay. All right, and I get a legitimate answer. 18 cubic meters. So the volume of displacement was 18 cubic meters, which means that 12 cubic meters were above the surface and 18 below. And so that's another example. Sorry about the confusion on the 60,000. It happens. All right, I think one last example. Well, it's two examples, but sometimes, let's say that we had a shell, an infinitely thin shell, and we are looking for the mass of the shell. That's the unknown. The tension in this string is going to be 60,000 newtons. The volume is 30 cubic meters. It is completely submerged. So the fact that it's completely submerged, the displacement volume is equal to V. It is hollow, which means that there is a volume of 30 cubic meters, and inside that hollow is air filled with air. Now, the density of air is probably one of the few reasons why I actually bring the book. Viscosity, Bernoulli's equation. .29 kilograms per cubic meter. So given a tension of 60,000 newtons and a volume of 30 cubic meters, the balloon effectively is filled with air, which is at that density, and the shell is made of some substance which is infinitely thin, but does have mass. So the question is, it can happen. Don't nod your head at me negatively. So the question is, what is the mass of the shell? And you do the same thing that you've done before. You sum the forces. The forces are, you've got a buoyant force of the shell and the air. You've got MSG down, the mass of the shell times gravity. You have tension, which is the force applied by the string, and then the last force is the mass of air times gravity. So there are now four forces, 3 down, 1 up. I know we're in translational equilibrium, so the sum of the forces in the vertical is equal to 0. That leaves me with buoyant force up, mass of air, gravity down, mass of shell, gravity down, and tension down. All I'm looking for is the mass of the shell, so I solve for it. Mass of the shell, gravity, is FB minus MAG minus T. Therefore, mass of the shell is 1 over gravity, buoyant force, mass of the air times gravity minus tension. That gives me 1 over gravity, buoyant force, rho water, VG. I don't use D because it's completely submerged. The mass of the air, we got to use Swiss Army knife. Density is mass over volume. So mass of air is density of air times volume. So density of air, volume, G, minus tension. That gives us 1 over 10, 1,000, 30, 10, 1.29, 30, 10, minus 60,000. And that will give us an answer. And I get the mass of the shell is 23,961 kilograms. And so that's how you would do it. Now, there is one of the reasons why I did the problem is I want to show what if the substance, actually I'm kind of using it in the wrong phrase. What if the substance isn't air but vacuum? Redo the problem. So in this particular case, everything is identical except for one thing. There's no air in the sphere. It is completely vacuum. There is no mass in that sphere, which means that instead of 4 forces in the vertical, we now have only 3. And if there are now only 3, sum of the forces in y is equal to 0, which is equal to buoyant force minus MSG minus tension. Solve for mass of the shell. Mass of the shell, gravity, is buoyant force minus tension. Mass of the shell is 1 over gravity. Buoyant force is density of water, volume, gravity, minus tension. That gives us 1 over 10, 1,000, 30 times 10 minus 60,000. So it's 300,000 minus 60,000 divided by 10. And I get an answer, mass of the shell is 24,000 kilograms. So if we considered the volume of air, the mass of the shell is 23,961. If there was no air in it, it was 24,000. A difference of 39 kilograms. Now, 39 kilograms is that big of a deal if you are dealing with objects that are approximately 10, 20, 30, 40, 100 kilograms. So a 30 kilogram difference is significant. But if you were writing this according to your sig figs rule, the mass of the shell would be 2.40 times 10 to the 5th, or I'm sorry, 10 to the 4th. Just like this is 2.4 times 10 to the 4th. What I'm trying to teach is when you are working with substances where the density of one is significantly greater than the density of the other, you can ignore row 2. There are going to be problems in that problem set. Namely, if you've got an object filled with air and that object is underwater, you could ignore the air. You can just say it's vacuum. Because that subtle difference will A, simplify the equation, and B, give you an answer approximately the same value. We're all beginning to get an idea of how we grade on tests. I'm not a big fan of having sig figs and having the numbers precisely right, mainly because I know you guys are still plug and chuggers. And so you do one rounding, that error that you introduce by rounding is going to be significantly greater than this assumption, which changes the value by, let's just take 39 divided by 24,000. That difference is not even 0.2%. What do we know about Physics 223 labs? If you get within 10%, that's awesome. 20%, okay, we can forgive you. Why? Because you're a first-year physics lab student. Doing this slight change doesn't affect it much, and it's within tolerances of rounding and all that stuff. If row 1 is approximately row 2, I would say within a factor of 100, 50 to 100 to be safe, you must take into account all of it. So if the densities are dramatically different, we're talking like the density of air was 1 and change and the density of water is over or is 1,000. So it was off by a factor of like 700, 800 times. So you can effectively eliminate air and not worry about it. In this particular case, if it was air-filled or if it was a helium-filled balloon in air, yes, you do have to take that into consideration. Let's see. I got 11 minutes. I can do one last problem. Let me take a look. Let's see what we've done. Oh. I know what it is. This will help you with number 11. And it gives me an opportunity to introduce an idea. For those of you who are taking the MCAT, the OAT, the PCAT, these standardized tests, You've heard of something called a passage problem. A passage problem, what they do is they throw this 4 or 5 paragraphs of text, and inside the text is a physics problem or a biology or whatever that asks you to do several things. In my class, I did not intentionally do this. It just happened that it matched up with the MCAT. I call them hybrid problems. My idea of a hybrid problem is a problem that uses multiple sources of physics knowledge puts them all together and expects you to know how to manipulate them. The example that is a perfect hybrid problem, and it's a problem that we will meet several occasions. You have an arm, like a post, and it is there's a hinge at the wall, and there is a string. And the question that I ask is, well, what's the tension of the string? If you have a mass hanging off the end. And what I did in this particular problem is I have an R1, and in that part I call R2, and I gave you a value which I shall now call Y. And I ask for the tension. Now in this particular case, there is no water on that mass. Probably what will happen is I will do it without the water, and then tomorrow, I do have to make one change, I think. The change is that the mass that's hanging in the water is made out of aluminum. So what you're going to need to do is you need to look up in Wikipedia what the density of aluminum is. And we'll talk about why that's important later. But for the setup, it'll only take a minute or two. This bar, it's a torque bar problem. You've got this string which has a tension going in that direction. Now, this is acting at an angle, theta, and you can figure out theta because that is the inverse tan of y over r1. This tension has a tension in the y and a tension in the x. Here, there is an M1G pulling down that particular force. What we're going to do is we are going to make our rotation point the hinge at the wall and the bar. Because it's not rotating, because the wire is holding the bar and mass up, we know that the sum of the torques is equal to 0, which means that TYR1 and M1GR2 are our two torques. The signs to the right, up, positive, to the right, down, negative, would give us this. And so we can solve for Ty and get an actual number. And then after that, we know that if that's theta, that is theta. So sine of theta is equal to Ty over T, or T is equal to Ty over sine theta. And so you can get the tension this way. When you put this thing in water, I'll just say it in English and then tomorrow we'll work on it. When you put this in water, does that force get greater or lesser? Does it increase or decrease? If you lower that object into water, a buoyant force is introduced that's up. So what happens is effectively the rock gets lighter. And that force will decrease, which then decreases T. So what I would want you guys to do is work it out this way, and then tomorrow I'll show you how to adjust for buoyant force, and then you can do the problem again and then see how they work. That's it.